Hello there, thank you for joining me again today. Welcome to the wonderful world of RF electronics engineering. Here on the bench we have a second Motorola radio test set for repair. You might remember in a previous video, and if you haven't seen that, please look at the other videos that I do. We actually repaired one of these for another friend of mine some time ago, and we did a component level repair, several faults on that particular test set. Anyway, on the bench is obviously another one. I think this one's a slightly different variant to the one that I did for the other friend. This comes from a very good friend of mine who's been, I've known for a very long time, since I was a teenager. And indeed, he runs the local repeater group for our area. So he looks after all the amateur radio repeaters for the whole of our area. And I went over to his home fairly recently to visit him to do some duplexer tuning for one of the 2 meters and 77s repeaters, which I did a video on as well. Anyway, while I was there, he said, "Can you have a look at this for me, because this has stopped working." Now, he didn't exactly explain what was wrong with it, he just said it just didn't work. Now, I'm not sure if he's been inside it or what, but anyway, we'll have a look and see what we can do with it, seeing as this is another one that's come my way. Anyway, top and bottom of it is the guy, obviously, that runs the local radio repeaters for the amateur radio network in the area. He and I go back a very long way. I mean, going back to the days when, in the 1990s, when we were put a repeater up in our local town, and we built it from scratch, basically, this repeater. And we had a logic board in there, a kit form that we had to build and wire it all into this ex-police burn-dept UHF repeater unit taught through base station. We had to modify it and everything. And of course, back then we didn't have all this fancy test kit, you know, and I was actually bringing the repeater into work where I worked as an apprentice, as a radio engineer, to use the test equipment at work, because we didn't have any of this fancy stuff back then. And there's a story coming up about that a bit later anyway, about when we put the repeater in, and a horse that nearly killed us all. So yeah, that'll be interesting. But I'll do a video as well on the repeater station that he runs, and we'll video the radio tower and antennas and the equipment cabin as well and everything, and I'll go and do that as part of the handover of this back to him when we've fixed it. So yeah, he didn't say what was wrong with it. I think he's had numerous Motorola radio test sets over the years, and I think this is his one that he's been using. So we'll see what's wrong with it. We'll just power it up and see what happens. So we've got it connected in at the back on the mains. We've got some LEDs here that indicate it's in standby mode, and then let's see what happens when we power it up. So there's no fizz or bangs or anything, no smoke or anything, flames, nothing like that coming out of it, so that's pretty good. So I've got some kind of test pattern here, and just have a look, see what it does once it passes its self-test. Yeah, so it's a little bit like the other test set with the overdrive on the CRT. So we'll have a look at that and see whether or not, you know, that's down to adjustments or whatever. But yeah, everything seems to be it's switching between the screens. This has got text, which, if you remember the other video, if you haven't seen that, you'll find that there isn't any text on that video. That's a spectrum analyzer, I think. So it's looking good. Got pictures anyway, that's the main thing. You can select between these modes. They switch as well, so it looks like as if we've got any logic troubles or anything. We've got an attenuator. That seems to be adjustable. What have you? So yeah, so it looks like all the switches and controls seem to be working. I think we'll probably go through these switches and see what we can do. We'll just make sure that they function. I'll put a signal into it as well and other things as well. see if SigGen's working and what have in the RF section. But I think first of all we'll just have a look at the monitor, see if we can get this horrible lining to disappear, because that's got this tearing off again. If you remember on the other test set, if you haven't seen that, please watch the video, but we had this tearing here, this scan line that comes down from the top on the horizontal scan and it dips down, and we had that on the other one. I think on the other test set it went that way actually, but yeah, so all in all it's looking a lot better than the other one with regards to its functionality. It seems to be functioning. So looks like when I adjust that, that's the frequency's changing. I'm not sure. It's knowing how to operate it as well. And, yeah, we'll have a look at that anyway and see what we can do. We'll put an RF signal in and put it on spectrum analyzer mode first. See that it's measuring an RF signal, and we'll have a look at that tube, that CRT. So bear with me. Okay, so we've got the lid off now. We're just having a gander inside to see if there's any telltale signs of adjustments or anything, or any other work that's gone on with it. I can't see anything that stands out. All seems in very good condition. Everything seems as if it's all in situ and everything as it should be. There's nothing that stands out at the moment. Just a word of caution when you're working on these test sets, they're actually quite lethal. They are definitely something to be respected when you're working on them. We've got some very high voltages in this unit, particularly in the CRT section, as you would find on any device that has a CRT in it, as you can see with all the danger labels. Under this can here is the switch mode power supply unit, which consists of 4 PCBs. All these will kill you. There's no doubt about it. If you get your hands across these while the unit's powered up, it's half a day with the Undertaker. You will not come off lightly when you touch anything under this can. So if you remove this cover and you're working on the unit, you know, obviously the wisest choice is not to do that unless you've got the knowledge and the information in order to be able to repair components in that section. Obviously, word of caution there, not only that it can kill you, but indeed the charge in the capacitors can retain for quite some time. So even when the unit's been unplugged and disconnected from the main supply, there's still dangerous voltages here. So you have to be very careful when handling these PCBs. Make sure the capacitors are discharged. Never take anything for granted, obviously, when you're working on equipment like this. You know, always give it respect. And ideally what you want on the bench when you're working on any equipment is an isolation transformer. But make no mistake about it, an isolation transformer will not protect you from high voltages on the switch mode power supply. There are rectifiers and diode components that are mounted on heat sinks on these boards that have well over nearly 400 volts DC on there. Even with an isolation transformer, if you were to touch them, you would be killed. So, you know, isolation transformer is only to give part safety really in this respect. That likewise as well on the CRT side, we've got 4000 volts supply here for the CRT tube. I think there's about 2.5 kV on the board at the bottom there, 2500 volts. We've got high voltage power supply unit. You'll see we've done repairs on these in the other video. This is a CRT drive board here, so basically these potentiometers adjust everything such as the character, height, width, azimuth as well for the horizontal and vertical sync. All the focus and drive and brightness and contrast and everything's all controlled on these potentiometers. Then these are the system cards which are going in. So we have the RF section here. All these cards deal with the RF synthesizer, spectrum analyzer, signal generator, portions of the RF power meter, and then these are the audio and logic IC logic boards. So we basically got a processor and a coprocessor, system card for system options. Then we have a scope card, and then an analog synthesizer card, so for generating audio tones and DCS and CTCSS tones, etc. Obviously on the board at the front here, which is this section, this board here allows us to connect to the front cover where all the logic functions from the relays for switching different audio paths, etc., all down there. For switching on different functions and ports, etc., selecting different BNCs on the front cover, and all the logic there that connects to these switches, knobs and controls, etc., to invert the function into the microprocessor card, an MCPU system, and the keypad as well. So that's all read through that front board that's down here. So what we'll do, switch it on anyway. We'll do a bit of card jiggling to see whether we get any faults to appear, and then we'll take it from there. And then we might do some adjustments on this card. I'm not sure if anybody's been fiddling. That does look like an adjustment issue, to be honest with you, on there. I've tried adjusting these controls, which you'll see in a moment, so let's just switch it on. And these controls are always a bit tetchy, even on the other one that we did a repair on. So it's just going through its self-test routine, and then when it's done that, we'll see if we can adjust out any problems on the display using these two controls. One is a focus display and the other's intensity. So again, we've got this bleed through this line in here, and can't seem to get rid of that. Focus seems to work, so that's well out of focus there, and then we can sort of bring it back. And the brightness, yeah, that's oversaturating, and then minimal brightness is about there. So yeah, we'll have a look anyway and see what we can do. I trust the keypad works, but we'll see about that. So we can't adjust it out on there. So let's have a look at this potentiometer. It's not doing anything. Adjusting it. That's doing nothing. We'll have a look at the. Let's have a look here. It's doing very little. And the third one. Oh, there we go. Look. So it's fully on there or there. Got some weird stuff going on. And it's gone. So that was fully wound one way, that fully adjusted one way for some reason. So whether somebody's been in tinkering or what, I'm not sure, but yeah, it seems to be responding to the keypad entry. Let's have a look, see whether the focus works on the adjust the intensities. The little one, that's the focus. It's just a sweet spot on it out there, I'd say. It starts doing weird things then. There's only like a small adjustment on it, you know. Then the brightness. There we go. So that's full brightness. So that must have been the brightness control we were adjusting there, without looking at the manual. And I'm just trying to get the sweet spot with the focus. So it's well and truly out of focus. It's just right, tiny little sweet spot right in the middle. It's about there actually. It's a bit of a devil to sort of adjust it. But they always are on these test sets for some reason. They always seem to be out there. So let's have a look and see what else we can get. So here we've got modulation, spectrum analyzer. Right, spectrum analyzer. Can I adjust that? Adjust it. Or do I have to move it? Yeah, I have to do that. So like kilohertz. Right. Okay. Right, sure. Might be that the graphics is off over here. So what I'll do, I'll put it at 145 dead. And oops. We'll change that to 145.0. And we'll put a signal into it and see whether it's working on that frequency. Probably a quicker way of doing it than what I'm doing, but right, looking at the manual. Right, so that's on 145 megahertz dead. Right, I'm going to put an RF signal in on here, and then we'll adjust these attenuators, etc. See whether we can get it to read a signal, and then do some adjustments, I think. Right, we've got the front connector connected up with the N-type lead going up to the instrument of choice today, for the test being the 2968 Marconi IFR radio test set. So we basically got the frequency to set here from its default 150 megs to 145 megahertz, I think it was. So we'll just set that up to RF frequency 145 megahertz, RF gen level. It's at neg 80 dBm, but we'll just adjust it. It's more like neg 40 dBm. So that's there. We're all set to go. We've got the frequency. We've got 1K mod on at 2.5 kHz deviation at 145 megahertz. So let's see whether this spectrum analyzer works. So we've got 145.0. Not quite sure if they appear to be. Not sure why. Right, that's interesting. So is that down to the scope thing? Let's just have a look at these adjusters down here. Just going to adjust these again, just to see whether they pull the image across. Nope, nothing to do with that. Might be something to do with these two at the end. We'll see what we get. What? Adjust the horizontal thing. Yeah, something weird. Something weird. Let's have a look here. Change that to CW. Generate that's monitor. Oscillator modulation off. Spectrum analyzer. So let's just have a look. Can't see anything there. So it looks like we've got a problem. It looks like as if the spectrum analyzer itself doesn't seem to be going across there. Okay, so let's see whether we can get the signaling standard, external wattmeter, gen monitor. dBm input level. Is there a frequency counter? There is, yeah. There we go, look. Frequency counter. One frequency. reading 145.999, so I suspect it's input frequency. Looks promising, looks like it's reading the frequency. I'll just verify that by changing it on the 2968. So RF gen frequency 146 megahertz, and let's see whether it jumps with it. It doesn't. Don't know why that is then. Let's have a look. Unless it's to do with this. Interesting. It says there range something not at max sensitivity position something. One is frequency, two is period. Right. Have I done something wrong? Two is period or something? Ah, not sure what that is. Puzzled. Let's see whether I can get it to lock onto a frequency, which I don't seem to be able to. So, line standard, Duplex gen, center frequency 154. Spectral analyzer looks like as if it's off. Right, well let's have a look at and see whether we can get gen monitor. Put in 146 megahertz in 460000. So it doesn't appear to be picking anything up then on this port. If I adjust the RF Attenuator. We've got something here. Neg 46 dBm input level. So it is working that then. So it's picking that up. Neg 46, which is around about what it will be. Neg 4 to give it a few dBs. 146 megahertz. Okay, so now we've got its sensitivity. What about if I go back to frequency counter? It's picked up 146 megahertz there. So it looks like as if it's working. I'll change the frequency again on the radio test set to see whether we'll put it at 150 megahertz then. See if it changes with it. I'm not sure how long it takes for it to update that, but it just seems a bit strange. I'm not sure how it works. Might be me that's not understanding how that works. I don't think it's just a straightforward frequency counter, because it says count mode selection is 1. So 1. I'm not sure what that is. 2 is period. 1. No idea how that works, to be honest with you. Monitor CW, count frequency. Unless it only works with RF power. going in over a certain level, perhaps, I don't know. But we've definitely got a problem with the spectrum analyzer, but I'm not sure why. What's this here? Monitor, narrow, high. That's 1K tone levels, that's your external tones. So the oscilloscope section, this should be controlling that, the spectrum analyzer bit. So I'll just see whether we can improve on that. I think I'll put an audio signal in on the onto here, and then see whether the oscilloscope bit works, because it could be that, you know, it's something to do with that. Let's just manipulate these cards, see if we get anything to show up. Yeah, that's causing that light to blink sometimes when I'm moving that card. So I don't know, we've got a bit of a trace there. There might be something strange, some setting. I'll have a look at that and come back. Okay, it's an adjustment that I found that balances the scan, if you like, of the spectrum analyzer, oscilloscope and other functions, along with the text. And basically it's the third potentiometer down here, which I'll show you. But basically it balances the text with the spectrum analyzer readout. So that's the oscilloscope at the moment. We've got an audio signal coming in from the HP8920 radio test that we're using the F out to generate an audio signaling. So that's the oscilloscope fed in on there. So that all works with these controls which I've just set up, and they're all functioning as they should be. So that's fine. That's scope AC. That's IF. So that's the IF frequency that's coming out. External wattmeter. This is the dBm distortion. So that's again reading the AF level. Now monitor FM. That's monitoring the FM content. That's a frequency counter which seems to be working. That's the signalling standards. That's the RF memory, and this is the Duplex gen. So it's reading the modulation, deviation that's coming in from the IFR 2968 radio test set. So we can see that it's reading correctly, more or less. That's the spectrum analyzer. Now what happens is, if you adjust the third potentiometer along, which is this one, keep your eye on that. If it gets too much, it just zips off the edge of the display, and that's where it was before. It was right on the end. The text appeared correct, but the scope itself had gone straight off, you know, stage left. Now when I went back to these, obviously there's a trade-off between those bars coming across again that cover the display and the trace of the spectrum analyzer. So if I adjust this again, so we get those bars there, and then when we go back to spectrum analyzer, which is down here, that's calling me a liar, but basically it's that trade-off where you get the spectrum analyzer back rather, but then you don't get the text, you see, showing properly. It looks all terrible. So what you have to do is you have to turn the third potentiometer there, obviously follow the instructions in the manual where you can. So that's just gone, you see. If you turn it too far, you won't get any trace at all of the spectrum analyzer. So if you turn it right down so it doesn't cause an effect on there, and then we go back to the spectrum analyzer, which I think I've just done, then you don't get the trace. So what you need to do is go to spectrum analyzer, adjust the third potentiometer until you get the trace, but you've just got to finally adjust it so it's not too over. You don't want it brighter than the text that appears above. You want a nice mix between the text and that, because you can adjust the brightness on there anyway. Then when you go back to normal text, you shouldn't get the bars, you see, interfering. So here we're reading the RF signal that's coming in on the N-type, and then we're reading the frequency error, how far off frequency the RF carries. So I know with that reading what it says there, which is 25 Hertz or whatever it is, how many hertz that is, I'm not right sure what it says because I'm trying to view it through camera. 60 odd hertz off or whatever. That means a reference oscillator in the units on frequency, so it's not reading incorrectly. It says here we've got a minus 45.3 dBm input level, which is actually just a few dBs off, with the RF attenuator set at maximum setting there, so I might have to do some adjustments with that. But yeah, the spectrum analyzer, that's a modulation, which you might be able to see on the oscilloscope. So that's a mod that's coming in from the just trigger it. So that's a modulation content from the RF carrier. Obviously we've got wide and narrow switch, so that's wide and that's narrow, and then we've got high and low squelch, BFO for sidebands, etc. Got the volume, and the squelch control works as well. So that's all functioning. Let's have a look. Yeah, that's functioning. So I think we're getting ready now to spectrum analyzer's working. So I can adjust that. Also with this wheel here, that functions obviously. So that's there, that's all functioning. And there's that's the sweep, or what is the resolution bandwidth of the spectrum analyzer, as you can see. So that's functioning as well, so that's good. So I've got spectrum analyzer back. Obviously if I adjust the RF gen level, so if we go back to the RF gen level and then we start adjusting it at its level, oh dear, I've altered the frequency. There we are, 140, 150 megs dead, RF gen level. So then if I try and adjust the RF level, down, you can see that's following suit. So that's pretty good. So that shows the spectrum analyzer is fully functioning. Now these don't seem to affect the spectrum analyzer, any of these. It doesn't matter what you do with those, you do what you like with them. They're mainly for the oscilloscope section, the DVM in, and such like. So that's what that section's for. So I think now we're ready to the frequency counter. That's why it's moved with it. I wonder why though we're getting that distortion through and it's showing a massive frequency area, and it's because this had moved with it. This had auto-tuned. So I just need to just change that frequency, because when I altered the spectrum analyzer frequency, it then has a bearing on this. So I just need to put that back as basically I just need to stop messing about with it really. So that's 0, 0, 0. Right, so we're back with proper thing now. Frequency. So that's the spectrum analyzer. That's the modulation. Now, according to the IFR 2968, we're generating a modulation frequency of 1 kHz at a deviation of 2.5 kHz. So let me just see if I can focus that a bit better. Now, according to this, it's doing something wild. Oh, hang on. It has to be on narrow, that's why. It says we're doing about 6 kHz deviation according to that. So that's a bit out of kilter. We'll have to adjust that because it's saying here plus minus 6 point whatever kHz deviation, and I'm not aware of us sticking that kind of level out. So now that's interesting, having the oscilloscope plugged in with 1 volt coming in is affecting the measurement. So I think that's down to that, to be honest with you. So yeah, it's reading correctly then, plus 2.5 minus 2.5 there. Yeah, roughly 2.25, 2.5. So that's correct. The mod's right. So that's correct. So let's have a look now. There's the RF memory for recalling memories out of it. Signaling standard. There's the frequency counter, which is 150 megahertz there. So that's okay. So that's 1, 0, is it? They're memories then when you enter that in there. So now to get it to read the frequency, I think you have to go down and select 1 there or something. Not really sure how the frequency counter works. Bit of a pain in the backside really is the frequency counter. It's weird. I don't understand how the frequency counter works on this. Input frequency in hertz. So we'll measure transmit power as well. We need to do that. That's a distortion. So DVM mode. Plug the DVM in. So it's reading an AF level. So just trying to work out one is AC volts, is it? Oh, it's because that frequency is wrong, isn't it? That's right. Right, 150000. So that should be on that DVM volt thing. It seems to be functioning, but I'm just trying to ascertain how it works. Distortion synod, DVM input level. So it's getting the level, so that's okay. External wattmeter IF, that's the intermediate frequency that we're picking up from the carrier that we're putting into it with a signal on it. That's the oscilloscope, which is what we've got there. Which, if we can move the position up and down, and then alter that. So that's working. It's got DC. Right, so there's different modes as well. There's FM, CW and AM, SSB. So I might have to have a look at that. So we'll have a look at that. I think what we'll do now, check to see how much RF power that it can read properly before we go into the signal generator modes. So at the moment we're on monitor there, and we'll check that and we'll see whether the signal comes through. We've got an antenna connection here as well. We'll check that for sensitivity and an output there, because on this you can have single port or dual port, in out, or antenna for off-air monitoring. So we'll have a look at that on the spectrum analyzer, see what signals we can pick up and what have you. Right, we've got an external antenna connected here, just a whip aerial, again in the workshop. What I've done is I've set the frequency to 93.7 megahertz on the spectrum analyzer, which is a local radio station that's a talk radio station. A BBC radio 4, I think it is. So we've got that in at the moment. Obviously the maximum sensitivity of the antenna for peak it is there. So we're getting a good signal coming in. That's okay. Now you do that is you pull this control, so it switches to that, switches from there to there by pulling outwards. Now at the moment can't hear any speech coming through because we need to go to the monitor. So
this was like for you.
So that's the that's the modulation.
Since day one, I was alone at home with my grandchild as my daughter and her husband. I beg you for one thing, please close the skies, they are bombing. You may have noticed, especially there,
so we've got it on wide mode.
Not Ukrainian. That's really common for someone from the east of Ukraine.
So we've got it on wide mode, obviously, so we can demodulate the FM content. So if it's on narrow, so that's wide.
Feelings. Now we just hate them.
So that's all correct.
Hatred, as we have always been friendly towards Russian. We have never done any harm to them. We have never done anything ill to them.
So that's correct. We can see that. That's all running, so that proves that the antenna port's working as well. Okay, so I think the next test will be the card wiggle test now, to see if there's any data connections, dry joints, that kind of thing. So we'll start with the logic board, giving things a wiggle and see what happens. And nothing there with that one. Just made a relay go. Nothing too much with that one. So we'll just clean these boards anyway, to be honest. See whether seems to be staying stable anyway. It doesn't seem to. Oh, it's locked up. So obviously we've got a card problem somewhere. So we'll switch it on again, so we can get it to come on. So I think it's a case of just doing some cleaning and re-soldering through joints, things like that on the logic board, which is a common problem on these. As you'll see in the last video I did, there was a major problem with dry joints. So let's see whether the functions work. Right, functions are not frozen at the moment. So let's see what happens when I wiggle this card back and forth. Let's see whether it's frozen the functions again now. Seems to be okay. This one. It's powered off. It's powered off. So it looks like as if we've got some dry joints on those cards as well. So that'll need further examination, the logic board. So it's just doing its calibration thing. IEEE calibration, so that's there. Functions are still working, so that's okay. Right, we'll test now on the spectrum analyzer on the radio test set to see whether we can get this now to send a signal out and see what level that is, accuracy, modulation, etc. So bear with me, we'll just set that up now. I've noticed as well that this test set's coming up with a strange error every now and then. It comes up battery low on the screen for some reason. I don't know why that is, even though it's not on battery, external battery mode. It's there you are, look, just appeared then. So I don't know what that's about. Maybe it's dry joints on this board here, makes it think that the battery low. It's run off a battery or something. That wasn't coming on till we wiggled those boards, so got a funny feeling that's associated with that. But interesting. Right, so we'll flick that now, that switch to generate, and morning battery low again keeps coming on. Right, modulation, high low image, Duplex gen is on. We're connected to the antenna output port here. That's set there. Let's go to Duplex gen. Right, frequency 150,000 megahertz, and the output level is obviously controlled on here with this attenuator, so we need to just look at that. The spectrum analyzer now coming out, just to see what that is. Now we've got a tone modulation is continuous, private line DPL, 1 kHz tone signal is there, and it shows the deviation. As I adjust this control, it'll show the deviation. So we'll set that at 2 kHz. roughly. If I can get it to balance out like that. That'll do it. 2Ks. We'll see whether we can. We've got that there, 150 megahertz. Right, so if we go to the trusty IFR test set, spectrum analyzer, and we go. We'll put auto tune on, but I think what I need to do is just TX frequency 150 megahertz. And so far I can't see anything there, but let's just go to full screen, expand, and alter the RF level. Right, that's minus 50 dBs. We're allegedly generating a frequency of 150 megs according to this test set. So let's see if I can. I can't see any generation. I'm just adjusting this control here. I'm not getting anything there. So duplex gen on or off. I'll leave the duplex gen set to off for the moment. We're on FM, we're in generate, we're on what is duplex gen. So let's go to just the gen monitor on its own. 150 megs. Digital private line. RF level minus 20. Now it should. Now we are getting something jumping about on there now. I'm adjusting. Right. So should I switch that to off then for the tone, so we haven't got any mod at all? That might be a good idea. Yeah, so we've got the level there. So according to that, we can adjust the RF level up and down with this control as well. That control adjusts the RF level. So that'd be min and max. And likewise, as you adjust this control, the level appears to change there. So that is, let's set that at minus 20 dBm. Let's see how accurate the SIGGEN is then. Minus 20 dBm. So if we just adjust this and then put the markers on, move the marker and get that marker to go up there, right to the top, and that's pretty accurate. So we've got minus 20 dBm, marker 1, which is there, so the SIGGEN's giving out the right level. So that's okay, quite happy with that. So I'll just introduce the mod, just narrow it up. Right, we'll turn the mod on now by flicking the continuous switch. And we've got the modulation content. Now what I'm going to do is I'm going to go to TX test on here, and I'm just going to have a look to see what modulation it's going to give. Bar charts. So it says 1.43 roughly kilohertz. Now I'm just going to put the bandpass on for speech. Basically 300 Hz to 3.4 kilohertz, and we've got 1.4 Ks. So that's saying there it's doing, it says it's doing 2. Interesting. So with that then, the level, deviation, so that needs adjusting. So deviations out. It says +7, -7 there. And that's quite out, because it's actually I'll adjust it so it's 2 kHz deviation on the radio test that I'm using. And here it says it's doing plus or minus 8 kHz deviation, you know, so it's way off the mark if that's the case, because of course we've got plus or minus 2 kHz deviation, so that needs adjustment. So, you know, just minor things really. That's interesting. Now then, it might be me. I might have set that up wrong, because that there says it's the code synth level. Well, that will up here somewhere, so that affects this deviation measurement. So if I adjust that, you can see I can adjust it. So if I wind that to minimum level, now we've got the correct modulation reading. We've got 2 kHz plus or minus 2 point something, 2.2 and 2.16 there, and then we're near as damn it on there. So that's correct now. So it just shows you I can lead yourself off down a garden path. So let's adjust that then. So it says 4 kHz deviation there, and then we're doing 3.84, so it's sort of within spec. It could do with being a bit better, but it is in spec. Let's adjust this control so that we get 5 kHz deviation. So that's just over 5 k's deviation. It's so difficult to adjust it. So that's 5 k's, and then we've got 4.78 k's, so that's doing okay. So we're okay with that actually. I think we're doing okay with that. We don't need to adjust it as such. If it ain't broke, don't fix it. So that's alright. So I think next measurement is TX power now, to see if it's measuring correctly with transmitter power. So that's what we'll do next. Okay, we've got our trusty radio set up, our little VHF UHF dual bander, which we've got connected in here on the RF input port. We're only using that as a general rule of thumb at the moment, just to see what the power is. I've got that radio set to 430 megahertz down there, and this is set to 430 megahertz bang on. So let's have a look at the transmit power now and see what it's doing. So let's have a look. Yeah, it's according to this, it's doing, I think it's 10 watts more or less there, 9 point something, 10 watts. 1 2 3 4 5 5 4 3 2 1. It's reading deviation on the bottom bar graph, and it's giving us a frequency error there of what that transmitter's doing. Now if I just go down to modulation, we should be able to see our speech. 1 2 3 4 5 5 4 3 2 1 1 2 1 2. That's set to, should be at narrow. 1 2 3 4 5 5 4 3 2 1 1 2 3 4. So that's all there. Let's just go back up to gen monitor. 5 1 2 3 4 5 5 4 3 2 1 1 2. So it's doing 10 watts, say there, plus 40 dBm roughly. Right, so what we'll do, we'll unscrew that from the front of here, and we'll just make a power comparison measurement with the HP8920 radio test set. So we'll just move this cable over to here on the front of the HP8920. HP radio communications test set. Just make sure that's tightened up. SMA, select TX test. We'll leave it on auto tune. So let's have a look, see what we're getting there then. RF power. So it says we're doing about 13 watts on transmit. So it's a little bit out then, is the Motorola need adjustment. About 12.8 watts now, TX power. So that just shows it's just a little bit out of kilter. Be interested to see what it's like on VHF. Obviously when we're doing RF power measurements, we do them across the entire frequency range of the instrument, and I've got some designated amplifiers that I use for doing wideband RF power measurements. So it's just a rule of thumb really, is that it's nothing too major. It's only a couple of watts off. So looking good so far. It does have a power off problem, this. Occasionally it will just power off, and I found it's the logic boards, when you move them it'll just die. So I think that's the original problem with this, to be honest with you. A bit of adjustment plus the logic cards. I think we just need to do some resoldering on logic cards like we did on the other test set, and put it back together, and it should be okay. So that looks good at this stage. I'm quite pleased so far with the basic adjustments that we've done to bring it back. The CRT, how it should be. Then on top of that, we've found that by moving the card here, then you can just get it to power off. Occasionally it's doing weird things like that. See, as I'm moving that card about. So it'll be a case of re-soldering that, I think, and then we'll go from there. Right, so we've removed the logic cards now from the machine. Basically, with two cards, we've got the main processor card, which goes at the very first slot on the far right of the instrument when the screen's facing towards you, and then we've got its daughter board as well that it shares a data bus with, which is this board here. And as you'll see from the other video that I did with the repair on that, a lot of these through joints all need to be resoldered, and it is a very time consuming job, but it's well worth doing. But again, these through holes on the top of the gold tracers here all need to be redone. And I think, looking at that, could be wrong, I'll just zoom in and see, has there been some leakage from those capacitors there, because this looks slightly discoloured. So it could be that we've had some electrolytics that have leaked, and the leakage has gone down. Although I might be clutching at the straws, but I'm definitely going to be looking at those, because there's some signs of corrosion just here on these gold pins. So they're more or less in line with these capacitors. So it could be that these caps have leaked, so I might need to replace these, and it's contaminated the track, obviously. But again, these little through holes here all need to be resoldered all the way around as you flex the board. You can find dry joints by using circuit freezer. It's a little bit it's a bit Eve Robinson. You can get away with it sometimes by spraying the board with circuit freezer, and the ones that have got the dry joints don't defrost as quickly as the ones with the proper solder through hole there. Looks like a little toroid inductor. But to be honest with you, it's also, while the board's in situ, if you could get to it, you can spray circuit freezer, and as the board expands and contracts with the circuit freezer in a given area, you can try and pinpoint where the dry joints are. But again, it's so difficult sometimes to find the faults with that technique, so I just resolder the whole thing really. So I'll just go through resoldering all the component legs, all the thousands of legs that there are there, all the through holes, and I will do those, you know, resolder them and go through the whole board like last time. It'll take some time, but I tend to do it in sections, you know. I'll do that section first, then that section, and then I'll do, you know, I'll break the board up into 4 parts. This board exactly the same, except there's more on it really, insofar as chips. So we've got some UV proms where the firmware and software of the instrument will be held on, with some RAM memory, EEPROMs. We've got other logic ICs, gate arrays, NAND and AND logic, etc. Microprocessor with a clock crystal, 3-volt backup battery for the RAM. So again, same process, resolder the through holes all the way around the board, and all the chip legs as well, so resolder those as well. So it's quite a few hours of work in this, but again, not to be rushed. Need to take time when you're doing these things, you know. It's not a mad dash to the finish line. It's more about the journey rather than destination, and just methodically go through the board as best as possible, resolder everything you can see. Again, I'll section this board off into quadrants so that I can concentrate on one area of the board at a time, so I'm not missing things. So that's what I'll be doing. And again, clean these gold connectors up. It's really important when you clean the gold connectors. I use like a contact cleaner rubber, which then just it's mildly abrasive, and it just takes the dirt and crud off the gold without removing the gold. Quite a lot of people I've seen use these really abrasive sort of fiberglass pens or whatever, wire wool, and it takes off the gold as well. That's not what you want. You want to retain the gold, and then just resolder and clean the contacts. There's definitely some contamination here come from these capacitors, so these capacitors may need to be changed. I'm going to investigate those further. I've got spare capacitors in stock, so I can do that. Other than that, yeah, I think it's just basics. I've taken a photograph of that board when it was in situ in the instrument, so I know which ribbon connectors plug in here, because that can be they can be accidentally plugged in the wrong way around. And same, there's a ribbon cable that connects there, what orientation that was. So again, when I put it back together, I should be able to reseat everything back in the original positions. I'll remove the UV proms on these sockets, and I'll clean the legs of the pins on these, because often you get corrosion on them and tarnishing on the pins, so they'll be reseated back in the sockets. And the same would go for this prom here. And we'll do some capacitor replacements, I think, as well as resoldering works. They've definitely leaked. So back soon when we're going through the process of resoldering. Right, here we are again. We've got the board ready now. This particular board is the daughter board to the main processor, which is this one. But quite a lot of the time, these through holes that are just at the top of these gold tracks go dry joint, as well as all the other ones. But basically, all I do with these is just get the flux. This is a water-based flux, so it's nothing nasty, no harsh chemicals or anything that are going to cause any long-term health issues, things like that. So it's a more gentle type instead of what used to be used years ago. And just give it a good this sort of area as well, I think. And do it in little patches, basically. And that's the thing with this, you've got to be patient. You just got to do what you can, and resolder as much as you can, and just work round the board, doing things in stages, basically. That's all you can do. and 9 times out of 10 you'll get it fixed. So I'll just give this a bit of a clean, and then we're ready. Now some of the through holes have got little holes in the middle of them. The solder blob has got a blob mound on it, and then there's a little pinhole in the middle of it. They tend to be the ones that are the driest out of them all. But I just apply a little bit of solder. I do both sides of the board to make sure that the solder flows through from one side of the PCB to the other, and that helps then ensure that the solder's gone through both sides to link the top and bottom sections of the boards together, and then that will more or less guarantee a successful repair then. Otherwise you could solder it and not actually carry out a thorough repair. I think some products that Motorola did used to use through hole, they were like pins that went in the through hole. There's a lot of kit out there, particularly by Philips, other manufacturers of equipment that use it. It's like a little pin, and they shove it through the board, and then they solder both sides. So that Marconi radio equipment used to have a lot of that on. So basically we're just making sure, you know, that these are soldered. These don't have those pins though that go through the board, so naturally it makes it more prone with just natural solder for them to break, crack, and then obviously get these bad through hole joints. So we'll just have a little break for a moment while I just re-alter things. We'll just orientate the board now so we can carry on with the rest of it. Just put a bit more flux on just to try and make these solder jobs more effective. The thing with water-based flux as well is that it dries very quickly, and so you have to be fairly quick with water-based fluxes, that you don't hang about too long before you start soldering. Otherwise its effectiveness quickly goes off. So as long as you crack on within a few minutes of dealing with it, then that's alright. So some of these aren't too bad, these through holes, the look of them, but we're just soldering them all anyway, just so that we get them all. And not too much solder, just a tiny little bit, just to renew what's already there. And obviously don't keep the iron on for too long, otherwise we can have some serious problems if we do that. Don't want tracks lifting or burning up or anything like that. So, but when I get to one of the really auspicious ones that it's quite clear that there's some major problem with the solder joint, I'll show you on the camera in a close-up sort of arena. So let's see whether we can solder these, and that's that. Now this particular track here has got a few through hole solder joints, so one there, and one there. So I'm just going to give that a re-solder as well, just that lot. So there's a through hole just there on that side, just there. Looks like it's either a ground rail or a supply rail, and then there's just one just here as well, just there on the end, if we can get the solder to start flowing. Now once you start, it's quite therapeutic actually, is doing this. It's calm, it's therapeutic, you know, it's you get going, and you think you'll do things in sections, but in actual fact you end up going all over the board, simply because there's a, you know, you see one through joint, then you see another, then another, and then you think, oh, I missed that, I'll just solder that, and you know, and you do another one, and you see something else that you might have missed, and you think, right, I'll do that as well, and then you, before you know it, you're just diving around board anyway. So we've got some that are down here, the side of these resistor chain in the red package. I'm just gonna, let's see if we can re-solder that. Might be better orientating it that way actually, then I can see what I'm doing. So we'll just get the soldering iron down here, and like I say, we go around the back of the board, the underneath, the underside, and do the same there. And that gives us opportunity to do things, take excess solder off, as well as to you know, make sure that they're all soldered properly and it goes through the board right. So we'll just give it a clean onto this IC down here. It looks like there's an island coming out there. So as you can see, we've done quite a bit of soldering now already, just in this past few minutes. So this is all nice shiny solder. Obviously clean the board with isopropanol alcohol, but as you can see, there's a marked difference between the shiny new solder and the old solder. So, you know, again, looking to make things nice. So we'll have a look. Looks like potentially this board is in a much better state than the other board. Might be something to do with the heat, you know. Obviously it's getting hot when the temperature's going up and down from hot to cold, cold to hot, etc. And I can tell this one's tarnished because it's not wanting to take the heat. Is that particular one there? It didn't like taking the heat from the soldering iron, so that's a good sign that that one was particularly dry. The alloy properties had degraded, and it wasn't then conducting the heat from the soldering iron. So whereas these are quite quickly done, these, so confident that that one was a particularly bad one, and we'll just reflow those. There's some more down here as well, 2 more there, and then we've got a track again near that that's got a thick conductive material on it there, but yeah, we've got through joints on it just there. Just here as well, we've got some more through joints down there, down the middle of this, just there. So we'll just re-solder those. And then whiz round the board. I always just apply a tiny amount, not too much, just a tiny amount. It's looking good underneath. So we've more or less done this section already, or that section, just in that area downwards. So then it's just these sections above. So yeah, a lot of these ICs here have got the logic gate outputs on. I have to do some research what these are. These are 7531 chips, AD7531, that is, and that is, and so is that, those 4. These are MC14174s, that, and that. That's an MC 14174s as well. 174, that's a 14174, 174. So these are all logics. All those are all the same ICs. That's a 74 LS138 NDS. That is as well. That's quite a unique chip. So yeah, there's quite a bit of logic on this one. These are MC6821 PDS chips. That's an MC6848 8 PDS IC. So there's quite a bit of old logic on it. So we'll just resolder this section next and take it from there. Okay, so I just wanted to show you what we were talking about earlier to identify a definite dry joint. If you look at these islands here, you'll notice this one here in particular, this has got that sort of scab in the middle. Now if I zoom right in, you might be able to see that a bit better. But they tend to be the ones that have actually got, they're the ones that are actually the dry joints. Now you can tell sometimes using circuit freezer if, you know, this one's dry in comparison to its neighbours, because this will thaw out at a different rate to the rest of them when you spray them with circuit freezer. So that one there is looking particularly dry, but yet when you compare it against this one, for example, they're all uniform, so they're going to be okay, but we'll solder them anyway. But it's when you see things like that, and sometimes as well, like you might get like a little pinprick hole in the middle that's formed and there's a bit of corrosion in it, that sort of thing. Not sure if I can see any on here yet that are like that, but if I do see any, I'll show you them what they are. But that's definitely dry as that one, without a doubt. So we'll resolder them anyway. I also do the legs on the ICs as well, just to make sure that they're all nicely soldered and what have you. So yeah, but that's just a quick rundown of what is a dry through hole. Right, resoldered all the through holes now. I'm just on the process of replacing the electrolytic capacitors that were in, that seem to be leaking and contaminating this gold strip. So I'll just put one capacitor in now. I'm just in the process of removing the other, but trying to remember the polarity in which they went in. So I'm just doing that now, and using the pace desoldering gun to try and desolder the capacitor. Solder's quite dry. It's quite an old solder, so it's more difficult to suck up and that. So that capacitor's got the negative side going towards the other one, so I'll just remove it and put another one in. So negative side towards the other capacitor. That's the thing when you're changing components, you just got to remember which orientation they went in, otherwise you're in you know, go fizz bang when you turn it on. So that's that. So that's what we're doing now. We're just changing those these capacitors down here. We've got two replaced already, which is this capacitor and that one. We just replaced them with the other two. These are better quality caps that are going in with the good ESR. So we'll just get these two out now and then replace them. And that's this board done. But as you can see, all the through holes are done. They're all nicely soldered and all nice shiny, like they should be. And same on the underside of the board as well. All nicely soldered, as you can see. So not take too long to do it. So hopefully that should do the trick. There's a bit of looks like there's a repair that I've got to do down here in this corner. See if we can zoom in to find out whether we can. But you can see just there, I don't know if you can see it, just there's a bit of a tear, there's a crack in this print. It might be just difficult to sort of try and get the angle on the camera, but you might be able to see there's it's just physically cracked along there where my fingernail is. So I've got to redo that because this is an earth bond print that goes all the way around and connects off to various things, so it might cause issues. So we're just going to have to, there's only a tiny little bit in this bottom here that's making any contact. The rest of it's just a complete crack right the way through. It's actually got a mound on it as well. You can probably just see that on the camera. With shrinkage and expansion has caused that to sort of bow up and break. So we're gonna sort that out, because obviously we've got all these other earth connections going off it as well to different parts of the circuit, so that's important. So we'll just scrape some off and rebridge that across. Okay, so we've got these 4 capacitors out the board, and we've got them here, all these 4. So we're just going to check them on the meter to see what they've got. So we'll just change to capacitance and see whether we can read them on our probes. So we'll do the first one. Let's have the butchers. See if we can get onto it. So that's the negative side, and then this is a positive side. Let's just read that then. So these are 10 mic at 50 volt. So that's reading 5.18 microfarad. So it's obviously way off what it should be. So we know that's definitely stuffed. We'll try the second one now. Put that on the negative again, and then this on the positive. And what's this one reading? 5 microfarad. So again, lost half its value. This is the third one. Let's see what this is. That's not, again, 5 microfarad. And then the last one, which is this fourth one. See whether that's reading the same. And here we go, 5 microfarad again. So they're all leaking, and thing is as well, these were smelt like fish when I were desoldering them, so I knew that they'd been leaking. So obviously you know, they're a 10 mic at 50 volts. That's what reading they are anyway, 10 mic at 50 volts. But they're only reading half a microfarads. This is just a capacitance meter, not an ESR meter. I have a little ESR meter here, an LCR thing that I use, and the other meter is down there as well, but I just couldn't be bothered using that at the moment, simply because I know they're leaked anyway. There's no point in confirming what you already know, but just for your benefit, I just thought I'd show what the capacitance reading was of all those 4 capacitors, only reading 5 microfarad. So yeah, they obviously needed replacing. Okay, so we've got the logic board now. We've done the resoldering work and replaced the capacitors on this board. So onto this one, and as usual, I've just resoldered all these through holes down here, and now we're onto this section. So I'm just in the process of doing that now. Again, much the same as the other board. I've seen some dry joints already that definitely needed to be resoldered. So it's just a matter of time, obviously, just going through it all again, and just making sure that we solder everything that we can without shorting anything out, of course. Being careful not to touch adjacent legs with solder and then bridge them through poor attention to detail, and that should solve that. Now there was one capacitor that I replaced, which is this one here. That again was a 10 mic at 50 volts, so we put another electrolytic in its place, and that should solve that problem in case it was not doing its job. So we've got another cap here, which I'm going to look at in a moment to see what that one's doing. We'll measure that in a moment just to see whether that's a fault as well. Probably is. May as well blanket change them as we're going along. And obviously got the 3-volt battery there for the RAM. That's another through-hole that had a little pinprick hole in the middle of it, just that one there, so obviously that one will go in dry. This one looks okay, and that one does more or less. Just give it a bit more solder. And there's one just underneath this 3-volt battery right down there, which I'm going to try and get to. So we're doing okay. So I'll be back when we've soldered all that. Right, we've soldered it all. As you can see, all the throw-holes now are all nice, nicely shiny and everything all the way through. They're all being re-soldered. So all looks good. Have to wait and see how it works when it's inserted. So we'll just clean the board up, I think, now, and then we'll get any deposits off, like from that capacitor that was here. You can see that it's been discoloured just there because it's leaked downwards. So we'll clean all these with isopropanol alcohol cleaner. It's important not to use something abrasive that removes the gold, so just some liquid alcohol cleaner will do, and then we're not moving the gold off it. Okay, you might remember earlier in the video on the original daughter board of the processor that we were doing, this board, the one where we replaced the 4 electrolytic capacitors, I found on the rear down here a crack that went across the print. It had lifted, mounted in like a mountain, and then cracked across. So that's the repair that I've done. What I've done is I've used this this tool here to scrape off the coating on the copper to create a space over here, bare copper, and then I've flowed solder across that crack and flattened it down. So now we've got a very nice looking, decent electrical connection that obviously goes right the way across the board. So that way we're not having that problem with the earth plane being the ground plane from being disturbed or broken connection, which is obviously going to cause all kinds of issues on the instrument. Okay, well, we've got it back together and switched it on just to do a little soak test. Everything seems to be okay. I can wiggle these boards now and I don't get any crazy things happening, so that's good. And we're just giving it a bit of a soak test just to see whether we get any smoke or flames coming out the back. And I've just got to plug a little aerial on there and have a tinker with it, that's all, on the transmitter monitor. I'm going to just see whether we're going to listen to a radio station, that's all on it. So I think it'll be 0. Oh, we'll try 1 or 1.1 000 megahertz, and we'll pull that out to select this antenna. and because it's a broadcast radio station, we'll just need to set that switch there under monitor for wide, and we'll set the squelch level to low, or the image to low. You can select between image up and lower, and then I think just alter the input attenuator. So we're receiving a signal off the air. Let's try another one. 0, I think it's 90, 93.7, is it? 93.7.
South or southeast 6 to gale 8. Occasionally severe gale 9 at first, veering southwest 4 to 6 later. Showers, good, occasionally poor at first. Right on out to the middle of Galloway. Southeast 6 to gale 8, veering south or southwest 4 to 6 later. Rain and showers, good, occasionally moderate.
We've got the deviation measurement as well.
6 to 7, occasionally gale 8 at first, veering south or southwest 5 or 6 later. Occasional rain, then showers, good, occasionally moderate.
Seems to be working.
Lock foil to Collingford Lock. Southeasterly 6 to gale 8, occasionally severe gale 9 in North Channel, veering southwesterly 5 or 6 later. Rain or showers, moderate or good, occasionally moderate. Mull of Galloway to Mull of Kintyre, I think.
Spectrum analyzer signal as well, that's coming through. Okay.
Rain or showers, good, occasionally moderate. Mull of Kintyre to Ardnamurchan Point.
Modulation.
Southeasterly 6 to gale 8, occasionally severe gale 9 at first in south, veering south 5 or 6 later. Rain or showers, good, occasionally moderate. Ardnamurchan Point to Cape Ryan. Variable 1 to 3 at first in north, otherwise easterly or southeasterly 4 to 6, occasionally 7 in south.
That's the IF you see.
Rain or showers, good, occasionally moderate. Shetland Isles.
That's a modulation.
South 5 to 7, backing southeast 6 to gale 8. Rain or showers, moderate or good, occasionally poor.
Position.
And that completes the shipping bulletin. That about brings us to the end of our evening's broadcasting here on Radio 4. Our World Service colleagues are standing by with a short news bulletin. After that, it's the Science Hour, where they'll be examining the current rise of COVID-19 cases in Hong Kong. That's about it from me for now. Radio 4 will be back with Alan Smith at 5:30. Thank you for your company this evening. I'm Amanda Litherland here at Broadcasting House in London, hoping that you have a peaceful night wherever you are. Good night.
Yeah. So it seems to be working. Got the squelch on. So touch wood, things seem to be okay. We'll just leave it on sort test for a little bit longer. Doesn't seem to be showing any jitters at the moment. Just give it the usual bangs and taps, etc. Just see whether anything starts playing up. I'll leave it to warm up as well for a few hours, just to make sure that it doesn't do anything silly. I'm going to do a power measurement next. And just alter the RF power reading, because it was a little bit off the last time. If you remember, we connected an amplifier into the N-type socket, and then we read the RF power versus what is on the calibrated instruments, and there was some wattage difference between the two. Well, on this particular instrument underneath, it's a shame the fan's quite loud on this one. Under this module there's a couple of potentiometers, because that's where the RF input attenuator is in this section, and you can adjust the level but it would read in there. So I'm going to take that to bits next, and we're going to feed the amplifier in again and then do some measurements that way as well. So back with you in a moment. Now, if you remember watching the other Motorola radio test set video that I did, we had the same problem as what we have with this. Now, what I've done, you take out all the screws, obviously, to try and get this can off, because we need to get down to those two potentiometers that are just in there, these two. Anyway, cut a long boring story short, is I removed all these screws, obviously, on both sides of the instrument. There's other screws top and bottom like this one here that bolt through to this die cast metalwork, and you just think you've got them all out, and you can just give this a bit of a pull, and there's two screws beside the N-type socket as well that obviously screw into this module. So there's no other screws that I can see apart from what there is for this switch, but I don't think that's going to hold it back. Anyway, there's nothing on this side, and obviously I've undone the screws that are on this side, yanked that back, and there's nothing happening. So I've got a bit of movement on this, just a touch, enough to get these two screws out that were down here, because they were touching this die cast. However, this one that's you might have to just see in the corner down there, that little sod, that won't come out because it's behind that, just touching that bit of die cast there. You can probably just see it there. It's a real pain in the arse, and I can't get that out. It's one of those things, a bad design, and I had a bit of a rant about this in the last video, and I just can't seem to get that bloody screw out. So therefore that's got to stay no matter what I do. I'm not stripping the whole front of the test set off just to get to that. Well, the rest of them off, what I'll do is I'll bend this can up. As you can see there, I've got some purchase on it, and I can get a trimming tool in to those two trimming capacitors. And in the repair video for the repair manual rather for the attenuator, all we do is we give RF input power into the front on the N-type socket, and then we adjust one of those trimmer pots then to give a right reading on here. So that's all we need to do. But again, a very bad design is that. Whoever designed this in Motorola has clearly overlooked the requirement to get access to that. And yet I don't understand why they didn't just drill two holes in the screening cam in order to just get to those potentiometers. Because, you know, all the RF stuff's done a bit further on in another cam, which you can't get to. That's not RF, that board. That's just dealing with DC voltages and logic volts. That's all that's dealing with. So it doesn't need to have a screening can over that section. Could just have two little holes, you know, just so you can get to it. It's little things like that that really get on my wires. Why people, these so-called designers, how they can't even design that, you know, and just get the basics right, you know, and then everything else will just fall into line once you get the basics done. But some crazy ideas that these people have that design these types of instruments. Anyway, I'm happy I've got it up enough so that I can get access into the to those potentiometers. And then we'll just have a look at the manual now and see what that says about adjusting it. So there you go. Okay, now we're ready to do a TX power measurement on there, but before we do that, we set up the 2968 to inject a signal out into the amplifier, and then on the output the amplifier all the way up to the Hewlett-Packard test set. We're going to read the amplifier's output level. So we will just connect up the supply lead here, and we're receiving there, as you can see quite clearly on the display, 8.4 watts, call it. Okay, so remove the DC supply to that so that thermal heating doesn't affect the measurement in the time it takes us to remove this connector and put it onto the other instrument. So we're using a frequency of 300 megahertz, which is quite common on most test sets, especially the ones that cover 400 kilohertz to 1 gigahertz range. and we're obviously using low loss military grade RF coaxial cable with precision connectors. So we set the frequency on the I know it's upside down, to 300 megahertz, and we're going to see what RF level that shows when we connect up the I think we've got everything else set. I'll just make sure that's set to narrow, that one, in case we get any issues there. I think it should be set to FM as well. Let's have a look. Is it set to FM, CWAM? Yeah, that's all correct. Right, no problem. Right, we're ready to rock and roll. I'll put the supply onto the power amplifier. Let's see what measurement it's giving. Let's have a look. So power is 6.5 watts, I think it says there. 6.61 watts, which it says, yeah. So we'll adjust that accordingly. So we'll lift the lid up now and see if we can adjust it. Okay, well, we've got the trimmer in the hole, so we'll apply power now. Now we're just going to adjust the it's at 6.27 watts now, which is just indicated there. So we'll just adjust that for about 8.2 watts, there about 7, 8, 8.2 we'll call it. Leave it at that, 8.2 watts. Right, we'll do some checks now on other frequencies and see if that's linear across the frequency range. Okay, we've changed frequency now to 450 megahertz, and according to the Hewlett Packard test set it should be doing 4.5 watts, I think it is. Yeah, 4.7 watts at 450 megahertz, so that's okay. So we'll just do another measurement at another frequency, something like 600 megahertz, something like that. Okay, this measurement's at 600 megahertz, and it should be doing about 6 watts thereabouts, according to the HP Agilent test set that we've just used for reference. So we should be getting 6 watts. So I'm applying power now on the amplifier, and it's reading it said 6.8 watts, I think it was, on the Hewlett Packard. So it's doing about right there. We're just under 7 watts on the Hewlett Packard. So that's reading okay. That slightly high, but only a few hundred milliwatts. Nothing in it really, well within its error specification. I'm going to try it on some really low frequencies now, like 30 megahertz. See whether it performs well down there. Okay, the Hewlett Packard test set now says that it's doing 9 watts. So let's just plug it into the Motorola, and already we've got 9 watts there, 9.7 watts. So yeah, things are looking good. Looks like as if we've got some success. Right, so now we've done that, I'll just show you which potentiometer it was that I was dealing with. It was this potentiometer here that I adjusted in order to bring it in line. That's in the Motorola service manual as well on how to do that, which I'll go into and look at shortly when we do a story time coming up on how this test operates and what it works as. And there's some interesting information as well that I'll be sharing on the way the instrument works, because there's an assumption that certain things work across its entire frequency range, and that's not the case, as you'll find out when I do the story time on from the service manual as to particularly the frequency counter. A little bit strange, the frequency counter on this instrument. Okay, so we've got the test set back together now. It's all ready to just go through some final checks before we can pass it back to its owner. Just time for a story time now to have a look through the manual and look at the operation specification of it. There's some interesting information about the frequency counter as well, which a lot of people may not be aware of, which is this mode here, which is quite a strange mode, which you'll learn about in this. So we'll just have a look at the manual and then we can review the features of the instrument. Okay, before we look at all the specs of the instrument, I just wanted to excuse me, have a quick read at the frequency counter bit, because most radio test sets offer a frequency counter that works across its entire operating frequency range, which in this case on this instrument is 1 megahertz to 1 gigahertz. So I would have expected when we select the frequency counter option that it would naturally be able to read any frequency between that range on the RF input, the N-type, but that's not so. Anyway, I'll read this section out here about it. It's quite an interesting section. Now it says here, it says the frequency counter measures inputs in the range of 10 Hz to 35 megahertz. So it's not capable of reading up to 1 gigahertz as a frequency counter, which I assumed it was. But anyway, it's a 5-digit auto-ranging output is displayed on the CRT and allows precise measurement and setting of offset oscillators. 35 kHz to 455 kHz pager IFs, intermediate frequencies, PL frequencies and other external input signals. This function will also operate simultaneously with the generator or monitor receiver modes of operation. Frequency measurement of transmitted carriers and other signals higher than 35 MHz is easily accomplished with the frequency error readout in the monitor modes. So that's how it uses it then. It doesn't directly read on the frequency counter. It doesn't directly read the frequency readout of the RF carrier coming in, which I thought it did, which I always thought was a bit strange. I had this problem with the other test set that I repaired for my friend. If you look at the other video I did, I had a big problem there where I was trying to get the frequency counter to read properly, and it turned out that it wouldn't read frequencies above 35 megahertz for that reason, and I had to read the manual then to find that out. So it's been some time since I repaired that last one, so I just had to familiarise myself with that section. Okay, so we'll go on to the overall brief now of the instrument. Okay, so the section for the description of the instrument, we'll just have a look through that now. It says the communication system analyzer is a portable test instrument designed for servicing and monitoring of portable, mobile and land-based communications equipment. It says that operating over a frequency range of 1 MHz to 1 GHz. It says the unit performs the functions of signal generation, frequency, error and modulation measurement. It is also capable of a variety of tests normally associated with the following devices. So it lists spectrum analyzer, duplex offset generator, modulation oscilloscope, frequency counter, AC/DC digital analog voltmeter, an RF wattmeter, a general purpose oscilloscope, multi-mode code synthesizer, a synapse meter and a sweep generator. So the microprocessor section of the unit is a Motorola M6800 series microprocessor. permits keyboard entry of data, auto ranging of displays, fast frequency access, and permanent storage of often used frequencies and codes. Generator monitor RF frequencies, tone codes, and timing sequences can be programmed into a non-volatile memory, saving time and eliminating entry errors when one particular type of equipment is continuously serviced. The unit can be programmed to select the mode of operation required when first tuned. So for the display section, it says all functions generated or monitored are presented on an 8 cm by 10 cm cathode ray tube (CRT) in both analog and digital format, with the name of the functions being displayed. The CRT also displays control settings, eliminating the need for operator search of different equipment panels. Digital readouts are visually aided by the use of a continuously auto-ranging analog line segments, which are similar to the bar graph. Each has a baseline and calibration markers, in addition to the intensified segment showing the measurement. The user-selectable displays are listed in a column beneath the display heading on the front panel. Choosing a display is accomplished by pressing an arrow button below the column for up or down movement as required. When the appropriate arrow is pressed, the LED adjacent to the selected display illuminates. Function is selected in the same way, providing rapid, accurate changes in service capability at the touch of a button. System warnings. To aid the technician in servicing, visual warnings will appear on the CRT when certain overload or caution conditions exist. Displays warn of low battery power, overheating the RF load, or when a preset deviation limit is exceeded in monitor modes. This limit is entered in by using the keyboard and may be programmed from 0 kHz to 99.9 kHz with 100 Hz resolution. Functions. The following paragraphs briefly describe the major functions of the communication system analyzer. It says AM, FM and CW DSB signal generation. The built-in general-purpose signal generator provides continuous coverage of the HF, VHF, UHF land mobile spectrum for receiver testing. Many forms of external and internal modulation can be simultaneously impressed on the carrier signal for actual composite signals. The frequency range of the RF signal generator is from 10 kHz to 1000 MHz in 100 Hz steps. The output of up to 1 volt RMS provides sufficient amplitude to get through misaligned tuners and receivers, and is especially effective when changing a receiver's frequency. The high-level, clean output is available over the entire frequency range of the communication systems analyzer. The output frequency is referenced to an internal time base, which can be calibrated to the WWV standard. It says simultaneous modulation. Modulation is simultaneously available from an internal 1 kHz tone generator, a multimode code synthesizer, and from external inputs. The external modulation can be voice from a standard Motorola mobile microphone, which plugs into the front panel of the instrument, as well as a signal applied to the external BNC input. Separate controls are provided for independently setting up the levels of the 1 kHz tone, the code synthesizer, and the external modulation sources. The 1 kHz test tone is a convenient source of modulation for making synapse measurements. A mod out connector provides external access to all the modulation signals. Now for modulation display. It says the recovered audio waveform or audio used to modulate the generator carrier can be viewed on the CRT. It is used to graphically measure deviation and to aid waveform analysis. Sweep generator. The sweep generator mode provides an RF output that is swept in frequency across the band entered at the program frequency. A synchronized horizontal sweep for the internal oscilloscope allows filter characteristics to be easily determined. This is ideal for in-depth troubleshooting of IF amplifiers and filters. Synad metering. A comprehensive check of receiver performance can be made with a synad measurement. The analog line segment and display representation of synad appear automatically whenever the unit is in the normal generate mode. The only hookups required are from the communication systems analyzer to the RF input of the receiver under test, and from the audio output of a receiver to the instrument's multipurpose input. The measurement and appropriate servicing can then be accomplished without the need for a separate signal generator, synad meter or distortion analyzer. Multi-mode code synthesizer. It says the communication systems analyzer generates private line tones PL, digital private line tones DPL, and two-tone sequential paging codes and tone remote based signaling tones. All codes are available at the mod out jack, as well as being used internally to modulate the RF signal generator. This eliminates the necessity of using separate generators and oscillators for general servicing, setting transmitter deviation, or for checking tone remote based control lines. Timing sequences are also stored in the tone memory to provide fast setup and eliminate errors. User programmable timing sequences are also provided to allow the storage of non-standard or future time sequences. So now we look at the off-air monitor section now. The 1.5 microvolt sensitivity of the communication system analyzer receiver allows off-the-air monitoring and measurement of transmitter frequency error and deviation to 1000 MHz. A variable measurement accuracy. The off-air monitor function enables frequency parameter checks without leaving the shop, thus spotting system degradation early and keeping service costs down. Bandwidth can be set wide for off-channel signal location, or wideband FM or narrow for maximum sensitivity and selectivity. The IF display. It says when the IF display mode is selected, the communication system analyzer's receiver IF envelope is shown on the CRT. This allows a technician to quantitatively and qualitatively assess the amplitude modulation envelope of a transmitter. Systems and spectrum analyzer. It says in this mode of operation, the CRT displays a window of the RF spectrum whose bandwidth from 1 MHz to 10 MHz is determined by the dispersion sweep control. The center frequency of this window ranges from 4 MHz to 1000 MHz, selectable by entering a specific center frequency with the keyboard. This center frequency is digitally displayed at the top of the CRT screen, eliminating the need for an external signal generator and counter to provide markers. Once a signal is centered on the screen, positive identification is aided by switching the analyzer to monitor AM or FM and listening to the demodulated output via the built-in audio amplifier and speaker. The spectrum analyzer's center frequency can be scanned up or down at rates varying from 0.5 kHz per second to 5 MHz per second. Using the RF scan control, slow rates are used to precisely determine a subject signal's frequency, while faster rates are used for locating intermittent transmissions or viewing large areas of the spectrum in short time. Uses of the spectrum analyzer are intermodulation interference identification, IF and RF signal tracing, transmitter harmonics measurements, transmitter spurious checks, and receiver local oscillator radiation. RF burnout protection. At RF input levels above 200 milliwatts, in any operating mode, the input automatically switches to the internal 125 watt RF load, thus protecting the attenuator and the signal generator and monitor mode against damage from a key transmitter. If power above 200 milliwatts is applied to any mode except the power monitor mode, an audible alarm sounds and a visual warning on the CRT directs the operator to switch to the power monitor mode. So terminated RF power measurement. It says RF power is automatically measured when the communication systems analyzer is in the power monitor mode. The built-in RF load dissipates up to 50 watts for 3 minutes and up to 125 watts for 1 minute. If a high power transmitter should be keyed into the unit for a time long enough to threaten overheating of the power measuring circuitry, the audible alarm sounds and the CRT function is further enhanced by displaying an RF overload temperature warning. By simultaneous indication of RF power output, carrier frequency error and modulation all on the same CRT display. It then goes on to talk about inline power measurement. It talks about use of the Motorola ST1200 series Wattmeter elements in conjunction with the analyzer's external Wattmeter display provides measurement of forward and reflected antenna power on the CRT display. This capability eliminates the complex hookups and the additional instruments normally required for antenna measurements. Duplex generator. In this mode, the communication system analyzer simultaneously receives and generates the signals for duplex radio servicing. While generated and monitored frequencies are observed on the CRT in the 0 to 10 MHz range, the frequency set control tunes the proper offset frequency for the VHF and UHF bands. The 45 MHz mode provides a single offset for the 800 MHz range. A switch is also provided to select high or low side offset as required. The duplex generator provides enhanced capability to service equipment such as repeaters, car telephones, emergency medical telemetry portables. 500 kHz oscilloscope. The general purpose scope is ideal for waveform analysis in two-way communication servicing. Use it for viewing modulation signals, either internally or externally generated, detection of asymmetric modulation or audio distortion, and general purpose signal tracing and troubleshooting. And then the last bit, which talks about the frequency counter, which we've read, which goes off about telling that it only works up to 35 megahertz. So we know about that. The AC/DC voltmeter, it says switching to the DVM mode provides a digital analog voltage presentation on the CRT along with a corresponding dBm value. The auto ranging display provides full scale deflections of 1, 10, 100 and 300 volts. AC or DC measurement is selected on the CRT. The meter's wide dynamic range and 3-digit display are ideal for setting power supply voltages, checking bias levels and setting audio levels like the frequency counter. The DVM will operate simultaneously with generator or monitor operation. Power supply. The communication system analyzer may be powered by a variety of sources. AC at 110 or 220 volts, 50 or 60 Hz. DC from an external 12 volt source such as a service vehicle, or DC from an optional battery pack. Servicing can thus be accomplished wherever the equipment is under test is located. So then there's some accessories here that you can use. Microphone, Motorola oscilloscope lead. There's the Wattmeter adapter, which is this thing here. That thing, and then there's power lead, and that's about it. That's all she wrote. So, with a look of it, that's pretty much the rundown of the specification of the unit. So, quite an interesting little book. Okay, so we just cleaned it up now, made it look nice and pretty, spruced it up. We've generated a 600 megahertz signal, monitoring it. I can put the Duplex gen on, so it's picking itself up, and we can hear itself pick up the RF signal that it's generating. So I can alter the 1K tone, and we can see the modulation, the deviation as well. Flick that to wide, and then we can measure wide mod as well as narrow mod. That's all functioning okay. So that's okay. So yeah, it's good to go now. I think we've done all the measurements, set it all up, it's all working properly as it should be, and I'm very happy with it. I think we're doing okay, you know, and certainly plenty of use in it still after all this time. So yeah, I think it's time to get it back to its rightful home now, and then back to the user that had it originally. So yes, another good repair. I think we've managed to you know, get it going, and certainly improved it substantially. So with that, I trust it. If you want to tackle one of these repairs yourself, at least you've got some idea of how to go on. That some of the common faults on them are dry joints, obviously. There are component failures with Zener diodes and other problems that you get on them, as you've seen in this, well, the other videos that I've done on repairing of the other models of these. So depends on what fault you get and what condition they're in. But they are a good test set, been around since about 1980, I think, and at least you know, if you want to get stuck in and get repairing them and that, there's lots of service information available online about these. So there's lots of resources and schematic diagrams, and the service manual as well is available online. I've got a paper one here, which the guy who gave me the test set to repair gave me this manual. The differences between these manuals is a lot, and the different models, because there are different ranges of communications analyzer. So there's D models, A, B models, there's all sorts of different variants of these out there. I mean, indeed, the photograph on the front of this box here shows on the front of that there's no antenna socket here. You know, there's two BNCs and an N-type. It just basically shows one BNC and an N-type, whereas, you know, actually we've got two BNCs and an N-type on this model variant. So they're all different models of them. Obviously this is the A and R, A models rather, the 2001A and the 2002 this covers. So there are different ones, so you're probably best off getting the diagrams and everything from the internet if you're wanting to do any maintenance and alignments of repairs, etc. yourself, rather than try and buy the paper books, because the paper books are nice, but you've just got to make sure that you've got the right model number, that's all for it, and they're hard to get. I should be giving this book back to the chap who gave me the Motorola test set to repair anyway, so you can have that back. But yeah, good little test set, plenty of capability. I did a lot of things that were off video as well, so the video wouldn't be too long. I did a lot of RF measurements that you didn't see. I also checked the power supply inside. I went routing for obvious faults, things like bulging capacitors, resistors that were charred, all sorts of mechanical issues like poor edge connectors and things that needed cleaning. So I did a lot off camera as well that you haven't seen, but the video would have gone on for 4 or 5 hours if that had been the case. It does take a lot of time and patience to repair these. These instruments are not easy fix. They are quite dangerous to work on. The other thing about them as well is that there's a constant need to pull boards out, do component checks while it's out of the instrument, put the board back in, and that can be quite tiresome because the boards are quite tight to get in. Also, with these, if you don't have the extender card, which incidentally I don't have, but they are available, you can't really extend the card out the test set to work on it. So it's very difficult if you do get a component failure on you know, one of these instruments to try and fault find to that level, unless you've got another instrument that you can borrow from somebody, and then you can swap the cards out and then at least get it down to PCB level and then go from there. So you know, you're sort of 99% there already. So that's the only other issue. So if you've got radio clubs near you, or another radio amateur that's near you, or somebody else that owns one of these that's prepared to let you borrow you know, the unit to swap cards. There are slight differences on the logic board layout and the daughter board for the processor card. There's some additional cabling on some which isn't on others. So there are differences between them, but you just have to make sure whatever test set you borrow from somebody else to do checks it's the same model and not a variant, because they have different boards in them. So that's one to be aware of. But yeah. So with that, hope you've enjoyed the video. If you like the video, please subscribe. There'll be more of these. Once again, thank you very much for watching, and we'll see you again in the next one. So thank you, bye bye.